Good evening, and welcome in to the Science Files. I'm Madeline Rowe, and tonight we're going to take a long, steady journey into one of the largest questions in modern cosmology. What is the universe made of? We'll follow the evidence behind ordinary matter, and dark energy, from the oldest light in the sky to the galaxies turning inside invisible halos, and from distant supernovae to the expanding space between galaxy clusters. And if you enjoy these calm, evidence-based case files, please subscribe, and there'll be another one waiting for you soon. There are questions that arrive dressed as simple inventory: a shelf, a manifest, a label on a drawer. Count what is inside, write it down, close the file. But the universe has never been that cooperative. Its contents do not sit in neat bins, waiting to be counted by hand. Much of what matters most does not shine. Some of it leaves only the bend of light behind it. Some of it is known through the speed of stars at the rims of galaxies, through the bruised shape of distant images, through old radiation cooled almost to absolute zero, through supernovae that look too faint for the universe they were expected to inhabit. To ask what the universe is made of is to ask how much of reality announces itself directly, and how much must be inferred from pressure, motion, gravity, distance, and time. It is to stand before the largest possible evidence room and admit that the familiar portion, the portion that makes planets and lamps and paper and skin, is only a small fraction of the full account. The rest is not decorative mystery placed at the edge of knowledge. It is load-bearing. It shapes galaxies. It pulls clusters together. It sets the rate at which the scale of the universe changes. It decides, in ways still being tested, what kind of future the cosmos is moving toward. A tunnel begins by making room where no room existed. This case begins in the opposite way. The room is already there. The space is already expanding. The galaxies are already turning. The light has already crossed billions of years to reach the detector. The question is, what had to be present, seen, or unseen for all of those measurements to agree as well as they do? Back in my office, the lamp over my desk throws a warm circle across a folder with a plain label. What is the universe made of? Beneath it, in smaller type, someone has written normal matter, dark energy. The folder is thicker than it looks. It has tabs for Planck, nucleosynthesis, galaxy rotation, gravitational lensing, supernovae, baryon acoustic oscillations, the Dark Energy Survey, and DESI. The order is tidy, but the subject is not. A tidy folder can make uncertainty look better behaved than it is. All of it is ordinary matter. Protons, neutrons, electrons, atoms combined into molecules, crystals, polymers, fluids, vapors, alloys, tissue, paint, dust. This is the sort of matter that chemistry knows how to name. It makes the visible world and most of the tools we use to study worlds beyond it. It makes stars, once gravity gathers enough gas together and heat begins to rise. It makes planets from leftover disks, oceans from condensed volatiles, bones from calcium phosphate, window glass from silicon and oxygen, and the thin graphite smear of a pencil mark across a page. For most of human history, that seemed like a reasonable answer to the question. The universe was made of matter and light. The matter was what things were. The light was how we saw them. If some objects were too faint to see, better telescopes might help. If some gas was too thin to glow, different wavelengths might find it. The assumption had a practical modesty to it. The world may be difficult, but it is made of the same kind of stuff wherever we look. Then the accounting changed. I open the folder to the first sheet. It is not a photograph of a galaxy or a planet. It is a map of mottled radiation, a full sky pattern of tiny temperature differences in the cosmic microwave background. The colours are artificial. The information is old. Older than stars, older than galaxies, older than the first heavy elements. It comes from a time when the universe had cooled enough for electrons and nuclei to combine into neutral atoms, allowing light to travel freely through space. That light has been stretching with the expansion ever since. Today it arrives as microwave radiation, cold and almost uniform, but not perfectly smooth. Those slight variations are some of the best evidence we have. They are not large. They are temperature differences of only tens of microkelvin across a background of about 2.7 Kelvin. They look delicate on the page, but inside them is a measurement of the early universe precise enough to weigh its main components. The cosmic microwave background carries the imprint of sound waves moving through the hot plasma before neutral atoms formed. In that plasma, radiation pressure pushed outward while gravity pulled inward. Baryons, the ordinary matter made from protons and neutrons, added weight. Dark matter added gravitational wells without joining the radiation pressure in the same way. The pattern of peaks and troughs in the CMB power spectrum preserves those conditions. The modern baseline model built around this evidence is called lambda cold dark matter, or lambda CDM. Lambda is the cosmological constant, the simplest mathematical description of dark energy. CDM is cold dark matter, meaning matter that moves slowly compared with light when structures are forming and does not interact strongly with ordinary radiation. The model is economical. It does not explain everything. It does not identify the dark matter particle, and it does not solve the physical puzzle of dark energy. But it fits a wide range of cosmological observations with striking precision. The numbers often get rounded for public explanation. About 5% ordinary matter, about 27% dark matter, about 68% dark energy. Rounded numbers are useful as a doorway, but they can also make the results sound like a pie chart someone read off a cosmic nutrition label. That is not what happened. The inventory was reconstructed from evidence spread across time. The microwave background gives one set of constraints. Big Bang nucleosynthesis gives another. Galaxy clustering gives another. Supernovae, baryon acoustic oscillations, weak lensing, and cluster counts add their own pressure to the same model. The fact that these lines of evidence can be made to speak to one another is the reason the model has endured. I carry the first sheet with me and leave the office. The corridor outside is lit in a low amber strip along the floor, enough to see by, not enough to erase the stars through the narrow viewports. The ship is on night cycle, though night is only a lighting schedule out here. A soft vibration runs through the handrail. On the left, the archive wall gives a faint click as a storage rack indexes itself. On the right, a maintenance drone waits in its dock, inert except for a single green indicator. At the end of the corridor is the observation dome. I step through the hatch and the ceiling opens into glass. Not open air, not true sky, but a pressure-rated curve of transparent material with the Milky Way dragged across it in cold, uneven light. A galaxy is a poor object to look at from inside one. We see our own as a band, an accumulation, dust lanes interrupting star fields. We have learned its shape through radio maps, parallax, gas, masers, star-forming regions, and patient geometry. But in the dome tonight, it is enough to let the band of it sit above the file like a reminder. The visible universe is luminous in places, dark in more places, and measured most honestly by more than sight. The CMB came from everywhere, That is part of its power. It is not a beam from one distant object. It is a surface around us in every direction, the last scattering surface, the farthest electromagnetic light we can observe in ordinary terms. Before that surface, the universe was opaque to light, because free electrons scattered photons again and again. After electrons settled into atoms, photons could move through space, and the universe became transparent. The pattern left behind was shaped by a competition. Dense regions began to collapse under gravity. Radiation resisted compression. Matter and radiation oscillated together like a hot fluid. Different scales were caught at different phases of this motion when the universe became transparent. Those phases appear as acoustic peaks in the CMB power spectrum. Change the amount of ordinary matter and the peak heights change. Change the amount of dark matter and the gravitational scaffolding changes. Change curvature or dark energy, and the apparent angular scale changes. The pattern is a code, but it is not a code made by intention. It is physics with enough time to leave a signature. One reason the CMB matters so much is that it gives a view of the universe before galaxies complicated the scene. Later, stars explode, black holes feed, gas cools, galaxies merge, clusters heat plasma, and ordinary matter becomes messy. At recombination, the ingredients were more smoothly distributed. The physics is still difficult, but the scene is cleaner. Cosmologists can use that early pattern to infer parameters that would later be tested against the structure of the universe as it grew. The Planck mission measured the cosmic microwave background with enough precision to sharpen this picture. It combined temperature, polarization, and gravitational lensing information to constrain the parameters of the standard cosmological model. The result is not merely that the universe contains baryons, cold dark matter, and dark energy. The stronger point is that a specific mixture of these components produces the pattern of CMB anisotropies, the angular scale of acoustic peaks, the matter density, and a late-time universe that agrees with many independent datasets. There are tensions, especially involving the Hubble constant and some measures of structure growth, but the basic lambda CDM picture remains a hard thing to replace. I rest the CMB sheet against the dome's lower console. Outside, the band of the galaxy looks solid enough to touch, though it is mostly distance. The stars appear crowded because our line of sight runs through the disk. Between them is dust. Beyond them is gas. Around them is a halo. Through all of it, dark matter is inferred not by glow, but by gravity. But before the file moves into darkness, the ordinary matter deserves its own page. Back in the office, I place the CMB sheet beside a second page marked baryons. The word looks technical, almost cold, but the things it names are intimate. Baryons are particles, such as protons and neutrons, made of quarks held together by the strong nuclear force. Add electrons, and baryonic matter becomes the matter of atoms. It becomes hydrogen, helium, carbon, oxygen, iron, silicon. It becomes air and water. It becomes the starship hull around me, the paper in the folder, the tea in the mug, and the hand resting on the edge of the desk. There is a danger in calling this only 5%. 5% sounds like an afterthought, but that small fraction contains every star that lights a galaxy, every planet that keeps a record in stone, every known ocean, every cell, every instrument, every telescope mirror, every detector crystal, every old notebook, every observation dome on every imagined ship. The universe may be dominated by darker components, but ordinary matter is the part that gives the evidence a witness. The baryon page begins early, before stars, before galaxies, before carbon chemistry, before solid ground. In the first minutes after the Big Bang, the universe was hot enough and dense enough for nuclear reactions. Protons and neutrons could assemble into light nuclei. This was Big Bang nucleosynthesis, and it did not last long. The universe expanded, the temperature dropped, the reactions froze out. What remained was mostly hydrogen, a substantial amount of helium-4, and small traces of deuterium, helium-3, and lithium-7. Those traces matter. Deuterium, especially, is a good baryon counter. It is a hydrogen nucleus with one proton and one neutron. In stars, deuterium is fragile. It burns easily. In the early universe, its final abundance depended on how many baryons were present. More baryons meant nuclear reactions proceeded more efficiently, leaving less deuterium behind. Fewer baryons left more deuterium. So when astronomers measure deuterium in distant, old, chemically simple gas, they are not just measuring a rare isotope, they are checking the density of ordinary matter in the young universe. The strength of this evidence comes from agreement across eras. The cosmic microwave background gives a baryon density from the physics of acoustic peaks hundreds of thousands of years after the beginning. Big Bang nucleosynthesis gives a baryon density from nuclear reactions in the first few minutes. These are different clocks. They rely on different physics. When they agree, they make the ordinary matter count harder to dismiss. The agreement is not perfect in every detail. Lithium remains the difficult page in the file. Standard calculations predict more lithium-7 than astronomers infer from old, metal-poor stars. The problem has persisted long enough that it has become a named issue in cosmology and nuclear astrophysics. It may involve stellar depletion, nuclear reaction rates, systematic uncertainties in observations, or physics outside the standard assumptions. It is not a small footnote. It is also not enough, by itself, to erase the broader success of Big Bang nucleosynthesis. The honest version keeps both truths together. I turn the page and find the low redshift baryon census. This is where ordinary matter becomes less familiar again. If the early universe tells us how many baryons there should be, then the nearby universe asks where they went. Stars are easy to love and easy to overcount emotionally. They shine, so they dominate photographs. But stars do not contain most of the ordinary matter. Galaxies, groups, and clusters hold some baryons in stars and gas, but a large fraction is spread through diffuse gas around galaxies and between them. Some of that gas is photoionized intergalactic medium, traced through absorption lines such as the Lyman alpha forest. Some is warm-hot intergalactic medium, shock-heated as structure forms, traced by ions such as O6, or by broad Lyman alpha absorbers. Some may be hotter still, difficult to detect in X-rays. The matter is ordinary in composition, but evasive in practice. It does not gather into bright stars. It does not always glow strongly. It reveals itself when background light passes through it and loses very particular wavelengths. That image belongs in the ship. A beam of light crosses a long, thin volume of gas. Most wavelengths pass through. A few are absorbed by atoms or ions with the right energy transitions. At the detector, the spectrum carries missing lines. The absence is the evidence. A dark notch in a spectrum becomes a record of baryons spread across intergalactic space. I stand from the desk and take the baryon page with me toward the environmental bay. The environmental bay sits 2 decks below the office, near the section of the ship where comfort becomes engineering. The corridor narrows before the hatch, and the floor panels change from the muted fabric of the living decks to a ribbed composite meant for boots, spilled coolant, and the occasional maintenance cart with poor manners. When the door opens, the room gives back a steady, layered sound. Fans, pumps, water cycling through recovery lines, the faint electrical note of sensors checking the air more often than anyone on board checks a clock. This room keeps ordinary matter in circulation. Air goes through scrubbers. Water moves through filters. Trace contaminants are trapped, logged, and scheduled for disposal. Heat is pulled out of occupied compartments and routed toward radiators. The system is a small controlled argument against entropy, and every part of it depends on matter behaving in ways we understand well enough to trust with our lungs. I slide the baryon page into a clear clip beside the main atmospheric panel. The display lists oxygen partial pressure, carbon dioxide, humidity, nitrogen balance, aerosol count, volatile organics, water recovery efficiency. A ship is not a universe, but it does teach a useful lesson. Familiar matter is never merely familiar. It must be counted, placed, separated, combined, ionized, cooled, condensed, and watched. The same atoms that feel ordinary in a mug of tea become a technical problem once the room is sealed. Cosmology has its own sealed room problem with baryons. The early universe says how much ordinary matter should exist. The nearby universe asks where that matter is hiding now. If one counts only stars and the cold gas that glows or emits radio lines in galaxies, too many baryons go unaccounted for. The missing part is not expected to be in one dramatic object. It is spread through circumgalactic gas around galaxies, intergalactic filaments, warm hot plasma, and phases that require patient spectroscopy. The ordinary matter did not vanish. It became difficult to see. Some of the best evidence comes from absorption. A bright quasar shines across a long path through space. Between the quasar and the telescope, gas clouds and filaments absorb specific wavelengths. Hydrogen leaves Lyman alpha lines. Oxygen, in particular ionization states, leaves its own marks. Each line is a small interruption in the received spectrum, a record of matter too thin to photograph as a cloud. The gas may contain only a few atoms per cubic meter and still add up to a major cosmic reservoir because the volumes are enormous. I open a maintenance drawer and take out a spent microfilter sealed in a transparent sleeve. Fine grey dust clings to the mesh. The ship's filters collect what the room would otherwise forget: fibres, mineral grains, fragments of skin, tiny bits of worn polymer. In a closed cabin, ordinary matter cannot pretend to be invisible for long. In intergalactic space, the same lesson stretches beyond intuition. A particle density that would be called vacuum in a laboratory can still form a filament millions of light years long. Thinness is not the same as emptiness. The low redshift baryon census often divides ordinary matter into rough homes. Some is in stars and stellar remnants, some is in cold gas in galaxies, some is in the hot gas of galaxy clusters, some is in the circumgalactic medium, the extended gaseous halos around galaxies. Much is in the intergalactic medium, including photoionized gas and warmer, shock-heated material. The exact percentages depend on observations, assumptions about ionization, metallicity, temperature, and the correction from a tracer ion to the total gas. The file does not offer a single clean drawer labelled "All Missing Baryons Recovered." It offers an improving inventory. The warm-hot intergalactic medium is a useful phrase for this case because it carries the feel of ordinary matter pushed into cosmic conditions. Warm-hot means temperatures roughly from 100,000 to a few million Kelvin. Intergalactic means outside galaxies. Medium means matter spread thinly through space. This gas can be produced as gravity pulls matter into the cosmic web, heating it in shocks and as galaxies drive winds outward. It is ordinary matter processed by large-scale structure. The first surprise is that ordinary matter is only a small fraction of the cosmic budget. The second is that even this small fraction is not all in the bright places. The stars are the lamps, not the warehouse. A large share of the ordinary matter lies in forms that require ultraviolet spectra, X-ray searches, simulations, and statistical corrections. The familiar ingredient becomes unfamiliar when spread across the scale of the universe. I put the filter back and moved to the water recovery panel. A thin column shows the day's reclamation efficiency. Water is a patient substance on board. It leaves a cup, enters the air, condenses, runs through membranes, returns to storage, and eventually becomes tea again. In the cosmic story, hydrogen is patient in another way. Most hydrogen nuclei are protons formed in the earliest moments. Some are fused in stars. Some remain in gas between galaxies. Some become part of molecules, planets, oceans, and organisms. Oxygen arrives much later from stars. Every sip of water is a partnership between the early universe and stellar history. The baryon folder needs that distinction. Big Bang nucleosynthesis made mostly hydrogen and helium, with small traces of light isotopes. It did not make the oxygen in water, the carbon in organic chemistry, the silicon in rock, or the iron in steel. Those elements came later. Baryonic matter includes heavy elements now, but the early baryon density is measured through light element production before stars had made those heavy elements. The atomic richness of the present universe is a later chapter written inside the same ordinary matter budget. I leave the environmental bay and follow the service corridor toward the aft observation blister, a smaller window set behind shielding ribs. It looks out along the ship's flank rather than forward. From here, the stars are partly blocked by the geometry of the hull. A faint reflection shows the page in my hand, baryons. Such a plain word for everything that can touch and burn and breathe. The file's next transition has to be handled with care. Ordinary matter is not the same as visible matter. Some ordinary matter is dark in the everyday sense. Cold gas may be hard to see. Dust can obscure. Planets do not shine by fusion. Dead stars can be faint. Brown dwarfs, rogue planets, black holes made from ordinary stellar evolution, and diffuse gas can all hide from optical surveys. But cosmological dark matter is not simply ordinary matter that happens to be dim. The total baryon density is constrained by the CMB and Big Bang nucleosynthesis. There is not enough ordinary matter allowed to explain the gravitational effects attributed to dark matter. That point is essential. Without it, the listener may reasonably wonder whether dark matter is just cold rocks, faint stars, black holes, or gas clouds. Some baryonic objects exist in darkness, and some contribute to mass. They do not solve the problem. The missing gravitational mass in galaxies and clusters requires a non-baryonic component in the standard model, a component that does not participate in ordinary light-emitting and light-absorbing processes the way atoms do. I tuck the baryon page under my arm and walk toward the lift. The doors open onto a small cabin with brushed metal walls and an old analog floor indicator, because someone who designed this ship had taste or nostalgia. As it descends toward navigation, the indicator hand moves from deck to deck. A ship always knows where mass is. It knows fuel distribution, cargo placement, ballast, torque, center of gravity. The universe gives us no central display, but it does give us motions. The navigation deck is dim when I enter. It wakes in a sequence: floor lights, table rim, side consoles, then the central holographic projector. A faint three-dimensional grid appears above the round table, followed by a model of a spiral galaxy. At first, the model shows only starlight, a bright central bulge, a thin disk, spiral arms, and a fading outer edge. It is a beautiful lie by omission. I set the file on the table and bring up the rotation curve. The expected line based on visible matter rises near the centre, then falls with distance. The observed line stays high, extending far beyond the bright disk. This is one of the classic doors into dark matter. Stars and gas in the outer regions of many spiral galaxies orbit too quickly to be explained by the visible mass alone, assuming Newtonian gravity and the usual mass distribution. The galaxy behaves as though it sits inside a larger halo of unseen matter. The solar system gives a helpful contrast. Most of its mass is in the Sun. The farther a planet orbits from the Sun, the more slowly it moves. Neptune moves more slowly than Earth. Earth moves more slowly than Mercury. That is what one expects when the central mass dominates. A spiral galaxy is not a point mass, but if most of the mass were concentrated where most of the light is, outer orbital speeds should decline. Instead, flat rotation curves show that mass continues to accumulate at large radii, where the light has thinned. Vera Rubin and Kent Ford's measurements helped make this problem unavoidable. They were not the first to find hints of missing mass, but their observations of galaxy rotation curves were clear, repeated, and influential. The edge of the visible galaxy was not the edge of the gravitating system. The stars at large radii were moving inside a deeper gravitational field than the starlight could explain. A halo of dark matter solves the broad rotation curve problem by adding mass outside the bright disk. The word halo may sound gentle, almost religious, but in this context, it is simply a distribution. It can be roughly spherical, extended, and much larger than the visible galaxy. The disk is embedded in it. The halo outweighs the stars. The bright spiral becomes the visible concentration inside a larger invisible structure. I rotate the galaxy model and dim the starlight until only the inferred mass distribution remains. It is a strange act, making the visible galaxy disappear to show what holds it. The display becomes a ghostly volume surrounding a centre that no longer glows. That is closer to the gravitational truth than the beautiful optical image. A galaxy is not only what shines. Rotation curves, by themselves, do not settle every argument. Modified gravity theories were developed in part to explain the relationship between visible matter and acceleration in galaxies. Some of those theories do surprisingly well on certain galactic scales. The scientific issue is not whether one can address one class of observations. The issue is whether a theory can explain the full suite. Galaxies, clusters, gravitational lensing, the CMB acoustic peaks, large-scale structure, cluster mergers, the abundance of light elements, and the growth history of cosmic structure. The standard dark matter picture carries that load better than its rivals so far. Those small-scale details remain active research. The navigation table changes to show a cluster of galaxies. The scale expands violently. Individual galaxies shrink into points inside a much larger gravitational system. Galaxy clusters are among the largest bound structures in the universe. They contain galaxies, hot X-ray emitting gas, and dark matter. The hot gas is ordinary matter, mostly ionized plasma, and in rich clusters it contains more baryonic mass than the stars in the member galaxies. This is useful because the ordinary matter is not all locked in points of starlight. It is a glowing collisional fluid that can be mapped in X-rays. Clusters were part of the dark matter story from early on. Zwicky's work on the Coma cluster suggested that the galaxies were moving too fast to remain bound unless the cluster contained far more mass than the visible galaxies indicated. Later methods used X-ray gas temperatures, galaxy velocities, and gravitational lensing to estimate cluster masses. Again, the answer exceeded the luminous matter. Gravitational lensing is especially important because it measures mass by its effect on light. General relativity says mass-energy curves spacetime, and light follows those curves. In strong lensing, background galaxies can be stretched into arcs or multiple images. In weak lensing, the distortions are subtle and must be measured statistically across many background galaxies. Either way, lensing can map total mass without requiring that the mass emit light. This is where the bullet cluster enters the file. I call up the image slowly. First, an optical view. Galaxies scattered across the field. Then the X-ray map. Hot gas glowing in a separated structure. Then the lensing contours. The inferred mass distribution. The power of the system is the offset. In this cluster collision, the hot gas, which contains most of the ordinary baryonic mass, has been slowed by ram pressure. The galaxies, being sparse and effectively collisionless on these scales, have passed through more readily. The lensing mass peaks are closer to the galaxies than to the gas. That separation is the heart of the argument. If the visible baryonic mass were the whole story, the gravitational potential should follow the dominant baryonic component, the hot X-ray plasma. But lensing shows the strongest mass concentrations offset from that plasma, aligned more with the collisionless galaxy components. The system behaves as if most of the mass is in a collisionless dark component that passed through along with the galaxies. The bullet cluster is sometimes presented too simply, as though one object alone proved dark matter in all contexts. The better version is stronger because it is more precise. The bullet cluster supplies a particularly clean separation between ordinary matter and inferred gravitational mass. It addresses some alternatives because the baryonic gas and the lensing mass do not occupy the same place. It belongs with rotation curves, cluster dynamics, CMB evidence, large-scale structure, and other lensing systems. It is one exhibit in a large case, but it is a memorable exhibit. On the display, the gas appears in one colour and the lensing contours in another. The difference is not decorative, it is physics. Gas collides and slows. Galaxies mostly pass through. Dark matter, if weakly self-interacting, also mostly passes through. That difference in behaviour gives the collision diagnostic power. The universe arranged a test in which components separated according to their interactions. I step back from the table and let the projection hover in the room. There is something almost forensic about it, not because the universe committed a crime, but because the scene preserves a sequence of events. Two clusters approached. Their gas clouds struck, shocked, and lagged. Their galaxies moved ahead. The gravitational mass traced by lensing did not remain with the gas. The aftermath records what the components did during the collision. The navigation deck is silent except for a faint projector whine. I take the dark matter page from the file and write 3 words in the margin: gravity without light. It is a useful phrase, as long as it is not mistaken for a complete definition. Dark matter may have interactions beyond gravity, but if it does, they are limited enough that it remains dark in the ordinary electromagnetic sense. It does not form shining disks. It does not cool efficiently by radiating photons. It does not collapse into stars. It forms halos and filaments, giving ordinary matter the gravitational wells into which gas can fall. This explains a strange partnership: dark matter helps ordinary matter become visible. Without dark matter, the tiny density fluctuations seen in the CMB would have had a harder time growing into galaxies quickly enough. Dark matter begins forming structure while baryons are still coupled to radiation. After recombination, baryons fall into those existing wells. The stars that later shine are, in this sense, indebted to the invisible gravitational structure that came first. I bring up a cosmic web simulation on the navigation table. The model begins smooth, then evolves. Dark matter gathers into filaments and nodes. Voids open. Gas follows, heats, cools, falls into halos, forms stars where conditions allow. The structure looks organic, but it is numerical gravity, hydrodynamics, expansion, and initial conditions. The web is not a metaphor in the survey data. It is the large-scale arrangement of matter. At the largest scales, the universe becomes statistically homogeneous and isotropic. That means no special place, no preferred direction, when averaged over sufficiently large volumes. But below that smoothing scale, structure is rich. Galaxies in groups and clusters, clusters connected by filaments, vast underdense voids between them. Dark matter sets much of that architecture. Ordinary matter lights parts of it. I close the simulation and open the candidate list. The file suspect board for dark matter has changed over time. Weakly interacting massive particles once held a central place. They fit naturally into certain theories beyond the standard model of particle physics and could produce the right relic abundance through thermal freeze-out. The so-called WIMP miracle made them attractive. A particle with weak-scale interactions and mass could naturally leave behind a density near the observed dark matter density, but experiments have not found them in the expected regions, and the simplest versions have been squeezed by direct detection, collider searches, and indirect searches. Axions are another major candidate. They began as a proposed solution to a problem in quantum chromodynamics, the strong CP problem, and later became compelling dark matter candidates. Unlike classic WIMPs, axions can be extremely light and produced through different early universe mechanisms. Their detection requires different techniques: resonant cavities, precision electromagnetic experiments, helioscopes for solar axions, and other approaches. The axion file remains open. Sterile neutrinos, if they exist, could also contribute to dark matter under certain conditions. They would not interact through the standard weak force in the same way ordinary neutrinos do, but could mix slightly with active neutrinos. X-ray constraints from possible decays limit their parameter space. Primordial black holes offer a different route. They would be compact objects formed in the early universe, not particles, and observations restrict many mass ranges through microlensing, dynamics, accretion limits, CMB constraints, and gravitational wave considerations. They remain interesting in limited windows, but they are not a simple replacement for particle dark matter across all scales. There are also self-interacting dark matter models, fuzzy dark matter models involving ultralight particles, asymmetric dark matter, hidden sector particles, and many others. The list can become a catalogue of names if handled poorly. The underlying lesson is simpler. The gravitational evidence is strong, while the microscopic identity is unknown. Dark matter is a measured role in cosmic structure, waiting for an actor in particle physics. I shut down the candidate list and sit for a moment at the navigation table. The galaxy model has left a faint afterimage in the glass. The starship continues along its route, adjusted by masses it can see and masses it cannot. Navigation has no patience for philosophical discomfort. If gravity bends the path, the course is corrected. Cosmology is slower, but the principle is similar. The universe tells us about its contents through behavior. The next folder tab is marked Acceleration. I gather the pages and leave navigation by the forward corridor. The ship's lighting shifts as I walk, a soft transition from blue instrument glow to the warmer tones near the inhabited decks. The acceleration file belongs first to the archive, where the old supernova plots are kept, and then to engineering, where the word energy can be handled with caution. I pass the observation dome without entering. The Milky Way is still there above the glass, wide and indifferent. The next evidence does not come from our galaxy. It comes from exploding stars in galaxies far away, seen when the universe was younger. The archive door opens with a low magnetic release. Inside, the shelves are still. I pull the folder labelled Type 1Ga Supernovae and carry it to the reading desk. The paper inside has the look of late 20th century cosmology. Plots with error bars, confidence contours, parameters named omega matter and omega lambda, and the beginning of a changed cosmic future. Type 1. A supernovae are not ordinary explosions. They occur in systems involving white dwarfs, though the exact progenitor channels can vary. Their usefulness in cosmology comes from their brightness and from the fact that their light curves can be standardized. A brighter, slower declining type 1, A, can be corrected differently than a dimmer, faster declining one. Colour corrections help account for dust and intrinsic variation. With careful calibration, these supernovae can act as distance indicators across cosmological scales. The method sounds almost simple in outline. Measure the redshift of the host galaxy. Measure the apparent brightness of the supernova. Use the standardized luminosity to infer distance. Compare the distance redshift relation to cosmological models. The work underneath is not simple. It requires photometric calibration, classification, K corrections, light curve fitting, dust treatment, sample selection, Malmquist bias checks, and comparisons between nearby and distant populations. The discovery of acceleration was not a casual reading of faint dots. It was an argument built through meticulous correction. In the late 1990s, 2 independent teams reached a compatible result: distant type 1. Our supernovae were fainter than expected in a decelerating universe without a cosmological constant. Fainter meant farther away at a given redshift. The expansion had not been slowing in the expected way. The data favoured a universe whose expansion had begun accelerating in the relatively recent cosmic past. The Supernova Cosmology project, using 42 high redshift supernova, found results strongly inconsistent with a flat universe containing matter but no cosmological constant. The High Z Supernova Search team, using its own sample and methods, also found evidence for acceleration and a positive cosmological constant. The agreement mattered. Independent teams, different analysis pipelines, same broad conclusion. The case for cosmic acceleration became difficult to ignore. I turn one of the plots under the desk lamp. A line that looks modest on paper once changed the expected fate of everything. Before acceleration, cosmologists could imagine the expansion slowing forever, perhaps halting and reversing if enough matter existed. With dark energy in the model, the distant future changes. If lambda remains constant, expansion continues accelerating. Distant unbound galaxies eventually slip beyond observational reach. The universe grows colder, darker, more isolated on the largest scales. The important point here is evidentiary. Supernovae measured the expansion history. They did not identify a substance. They did not capture dark energy in a bottle. They revealed that the simplest matter, only expectations, failed. The cosmological constant, already present as a possible term in Einstein's equations, became the simplest way to account for the acceleration in a flat universe with the observed matter density. I return the supernova plot to its folder and carry the acceleration tab toward engineering. The corridor slopes slightly where it follows the curve of the ship's internal pressure shell. Underfoot, the deck has a mild tremor from the power systems aft. If the dark matter section belongs to navigation, dark energy belongs uneasily to engineering, because the name invites the wrong image. Energy on a ship can be generated, stored, converted, wasted, radiated. Dark energy is not like that. The engineering room will help make that distinction by contrast. The hatch opens onto the main systems gallery. Reactor shielding rises behind transparent panels. Coolant lines bend in careful arcs. Heat exchangers sit behind grills with warning labels bright enough to be read in a power failure. Every part of the room is designed around control. Flow rates, temperatures, pressure limits, output, load, reserve. Dark energy offers none of this tactile machinery. It is a term in cosmological accounting, a name for the component or modification needed to explain accelerated expansion. In the simplest model, it is lambda, the cosmological constant. Lambda corresponds to an energy density associated with space itself, constant in time and nearly uniform in space. Its pressure is negative. In general relativity, that negative pressure gives it a repulsive gravitational effect on cosmic scales. Matter density decreases as the universe expands. Double the volume, and the same matter is spread thinner. Radiation thins too, and each photon also loses energy as its wavelength stretches. A cosmological constant behaves differently. Its density remains constant as space expands. As matter dilutes, lambda becomes more important relative to matter. That is why the universe can have a matter-dominated era when galaxies grow, followed later by dark energy domination when acceleration begins. The engineering gallery hums around me, full of energy that obeys conservation laws in familiar local forms. Dark energy's behavior is less intuitive because cosmology deals with expanding space-time, pressure, and the global dynamics of the scale factor. A constant energy density of space sounds almost like getting more total dark energy as space expands. But in general relativity, the bookkeeping includes pressure and the work associated with expansion. The intuition of a fuel tank does not apply. The physical puzzle is severe. If dark energy is vacuum energy, quantum field theory seems to predict a natural scale wildly larger than what cosmology observes. The observed density is tiny in particle physics terms, yet cosmologically dominant today. A value of 0 might have seemed natural in one sense. A huge value might have seemed natural in another. The universe gives us a small, non-zero value. That is the cosmological constant problem in its broadest emotional shape. A number that works beautifully in the sky and refuses to make easy sense in theory. Dark energy could be Einstein's cosmological constant, or something that behaves similarly, perhaps a dynamical field whose density evolves slowly. A scalar field model can have negative pressure if potential energy dominates over kinetic energy. Such models are often grouped under quintessence. They can ease some conceptual discomfort by allowing evolution, but they introduce their own questions. Why that field? Why that potential? Why these initial conditions? How does it avoid conflicts with observations? Another possibility is modified gravity. Perhaps the acceleration is not caused by a new energy component, but by gravity behaving differently on cosmic scales. This is an important idea to test, but it is constrained by many observations. General relativity works extremely well in the solar system. Binary pulsars, gravitational waves, black holes, and many cosmological contexts. A modified theory must recover those successes while improving the fit where needed. That is not impossible in principle, but it is difficult. I stand near the engineering status wall and watch the ship's power demand shift as the life support system cycles. Here, a change in output leaves a trace immediately. In cosmology, dark energy leaves its trace across billions of years. It changes distances. It affects the growth of structure. It influences the relationship between the CMB acoustic scale and the late-time universe. The evidence is not local heat, but accumulated geometry. The next part of the case requires a ruler. Not a ruler built in engineering, but one made by sound before atoms existed. I leave the systems gallery and head towards the cartography lab, carrying the acceleration folder under one arm and the older CMB sheet under the other. The path takes me through the ship's central spine, past junction boxes, sleeping compartments, and a narrow viewport where the stars seem to move only because I am walking. Somewhere in the ship, a clock ticks through an artificial day. Outside, the better clock is redshift. The cartography lab is dark when I enter. I ask for the large-scale survey volume, and the room fills with galaxies. At first, the display looks like a storm of blue-white dust suspended in 3 dimensions. Points appear in front of me, behind me, above the table, out toward the curved wall. Each point is a galaxy, or sometimes a quasar, depending on the survey layer I have loaded. The lab reduces them to marks because the true objects are too large and too detailed for the room. A galaxy with hundreds of billions of stars becomes a coordinate. A quasar powered by a feeding supermassive black hole becomes a tracer. A redshift becomes a distance estimate. A spectrum becomes a position in the cosmic map. The longer I stand there, the less random the points look. Dense knots emerge. Filaments stretch between them. Voids open where the points thin almost to nothing. The universe at this scale has a texture, but not a texture drawn by hand. It formed by gravity working on small initial fluctuations, with dark matter gathering first, ordinary matter falling in, gas heating and cooling, galaxies forming inside halos, an expansion stretching the whole field as time passes. This is the room where the word survey becomes physical. A survey is not just a list of objects. It is a measured volume of the universe, with selection effects, masks, redshifts, uncertainties, and geometry. It is a way of turning the sky from a picture into a data set. The galaxies in this room are not being admired one by one. They are being used as markers of a larger pattern. I place the CMB sheet on the cartography table and set the acceleration folder beside it. The oldest light and the late-time galaxy map belong together. Their connection is one of the best pieces of evidence in modern cosmology. The acoustic pattern in the CMB comes from sound waves in the early hot plasma. A related acoustic scale remains imprinted in the later distribution of matter. That fossil feature is called baryon acoustic oscillation, or BAO. The phrase sounds technical, but the physical beginning is direct enough. In the early universe, before atoms formed, ordinary matter and radiation were coupled in a hot plasma. Gravity pulled matter inward, radiation pressure pushed outward, sound waves travelled through that plasma. Dark matter, which did not couple to radiation the same way, helped shape the gravitational wells. When the universe cooled enough for electrons and nuclei to combine into neutral atoms, photons decoupled and streamed away. The sound waves stopped propagating through the baryons in the same way. A characteristic scale was left behind. In the CMB, that scale appears in the pattern of temperature fluctuations across the sky. In the later universe, it appears statistically in the clustering of galaxies. Galaxies are slightly more likely to be separated by a particular distance corresponding to that ancient sound horizon. No one looks through a telescope and sees a glowing ring around each galaxy. The signal is statistical. It emerges when millions of galaxies are mapped and their separations are counted. I asked the table to show a simplified acoustic shell. The display clears to a dark background. A single early overdensity appears as a bright point. Around it, a transparent sphere expands, representing the sound wave moving through the baryon photon fluid. At recombination, the shell stops growing as a pressure wave. Dark matter remains concentrated more towards the centre. Baryons have been carried outward. Over time, both contribute to the formation of galaxies, leaving a slight excess probability at the shell radius. It is an old ruler, not a ruler built by a civilization, not a measuring stick placed into space, but a length scale set by early universe physics. The value depends on the sound speed in the plasma and the time available before recombination. Once calibrated by the CMB, it can be used to measure cosmic distances later. At different redshifts, the apparent size of the BAO scale tells us about the expansion history of the universe. The first major detection of the baryon acoustic peak in the galaxy distribution came from the Sloan Digital Sky Survey's luminous red galaxies. The feature appeared at about the expected scale, confirming a prediction of the standard cosmological picture and giving astronomers a new geometric method for measuring distance. It was a powerful result because it linked late-time galaxy clustering to the same early universe physics that shaped the microwave background. The universe had kept the memory of its early sound waves in the positions of galaxies. In the lab display, the acoustic shell fades into a three-dimensional galaxy map again. The points return, now arranged with a subtle statistical preference. The preference is not obvious to the eye, and that matters. Much of modern cosmology lives below the level of visual certainty. The signal is not always a beautiful photograph. Sometimes it is a bump in a correlation function, a contour in parameter space, a likelihood curve narrowed by data that took years to collect. BAO matters for dark energy because it measures geometry. Supernovae tell us how brightness changes with redshift for standardized candles. BAO tells us how a known length scale appears at different redshifts. The CMB anchors the early ruler. Together, they constrain how the universe has expanded. A universe with only matter gives one distance redshift relationship. A universe with matter and a cosmological constant gives another. A universe with evolving dark energy gives another. The differences are subtle at first, then accumulate over billions of years. I bring up a redshift ladder along the wall, low redshift near the floor, higher redshift rising toward the ceiling. Galaxy samples appear in bands: luminous red galaxies, emission line galaxies, quasars, Lyman alpha forest measurements. Each tracer covers a different region of cosmic time and a different type of structure. The work is not merely to count galaxies, but to use them carefully. Their selection, bias, redshift errors, and survey completeness all matter. A galaxy is a tracer of mass, but it is not mass itself. Different galaxies form in different halos and environments. The analysis must account for that. DESI, the dark energy spectroscopic instrument, is built for this kind of mapping. It measures spectra for millions of galaxies and quasars, using redshifts to build a three-dimensional map of the universe. Its BAO measurements reach across a large span of cosmic history. With enough tracers, the ancient ruler can be measured at many redshifts, turning the expansion history into a more detailed curve. Recent DESI results have drawn attention because when DESI-BAO is combined with the CMB and certain supernova datasets, some fits show a preference for dark energy that evolves with time rather than a pure cosmological constant. This should be said with restraint. The evidence is not a final overthrow of lambda c dm. It depends on dataset combinations, assumptions, and ongoing checks for systematics. But it is important. The standard model has been strong enough that small deviations, if they persist, become valuable. They may be hints of new physics, or they may teach us about hidden problems in data, calibration, modelling, or selection. A careful reading lets the frontier remain a frontier. DSI does not mean dark energy has been solved. It does not mean the cosmological constant is dead. It means that the newest large-scale maps are precise enough to test whether lambda is still the best description when combined with other probes. That is a mature kind of uncertainty, not confusion. Pressure. I walk around the table, watching the survey volume rotate. The galaxies form a web that seems almost solid in places, though the distances between them are vast. The empty regions are not truly empty. They may contain dark matter, thin gas, stray photons, neutrinos, and the expansion of space itself. Still, compared with clusters and filaments, the voids are underdense. They are part of the pattern too. A map of the universe is a map of where matter gathered and where it did not. The next layer belongs to weak gravitational lensing. I bring up a field of distant galaxy shapes. At first, it looks like an ordinary deep image. Small ellipses, faint smudges, arcs of light, distant objects blurred by optics and distance. Then the software overlays shear marks. Each galaxy's apparent shape has been slightly distorted by the gravitational field of matter between it and us. One galaxy alone cannot tell us much because galaxies are born with their own shapes and orientations. Across millions of galaxies, statistical alignments reveal mass. Weak lensing is one of the most direct ways to map total matter. It doesn't ask whether the matter shines, it asks how space-time bends light. The challenge is that the effect is small. Atmospheric seeing, telescope optics, detector behavior, point spread function, noise, galaxy blending, photometric redshifts, and intrinsic alignments all complicate the measurement. A weak lensing result is therefore not just a pretty map. It is a disciplined analysis of subtle distortions protected against many ways of fooling oneself. The Dark Energy Survey used this approach over a wide area of the southern sky. Its Year 3 cosmology analysis combined 3 related measurements. Cosmic shear measured correlations in the shapes of background source galaxies. Galaxy clustering measured how lens galaxies were distributed. Galaxy-galaxy lensing measured how foreground galaxy positions correlated with the shearing of background sources. Together, these measurements helped constrain matter density, the amplitude of structure, galaxy bias, and dark energy parameters within chosen models. One of the live questions involves S8, a parameter related to the amplitude of matter fluctuations and the matter density. Some weak lensing surveys have preferred slightly lower structure growth than the value inferred from Planck under lambda c dm. The disagreement is not decisive enough to claim new physics on its own, but it is persistent enough to keep appearing in conversations about the standard model. Like the Hubble tension, it may point to systematics, or to physics beyond the baseline model, or to a combination no one has sorted out yet. The lab dims the galaxy map and shows a comparison panel, early universe constraints from the CMB on one side, late universe measurements from weak lensing and clustering on the other. A good cosmological model must carry information from one side to the other. It starts with early fluctuations, evolves them through radiation, matter, and dark energy eras, and predicts the amount of structure today. If late-time surveys find slightly less clumping than expected, the question becomes whether the growth history, matter content, neutrinos, dark energy, gravity, or observations need revision. This is where cosmology becomes less like a single answer and more like a network of constraints. The CMB tells us about the early universe. BAO gives distances across time. Supernovae give the expansion history through luminosity distances. Weak lensing measures the growth and distribution of mass. Galaxy clustering traces structure. Cluster counts add another growth probe. Redshift space distortions measure how velocities respond to gravity. Each method has its own weaknesses. The shared picture is built by comparing them. I open a wall panel showing the major probes of cosmic acceleration often discussed together. Type 1 are supernovae, BAO, weak lensing, and galaxy clusters. Supernovae measure distance through brightness. BAO measures distance through a standard ruler. Weak lensing measures mass distribution through shape distortions. Clusters test how many massive structures form over time. A balanced program uses several methods because no one method is immune to systematics. If all the evidence for acceleration depended on one kind of object, one calibration, one telescope, or one analysis method, the case would be fragile. Instead, cosmic acceleration is supported by a web of evidence. The supernova discovery was the turning point, but CMB, BAO, large-scale structure, and other measurements help make the case durable. I return to the table and call up a timeline of expansion. The curve begins steeply in the early hot universe, changes through radiation and matter domination, then bends as dark energy becomes important. The display adds markers: Big Bang nucleosynthesis, recombination, first stars, peak star formation, solar system formation, acceleration becoming dominant, present day. The timeline is compressed almost beyond meaning, but it shows one crucial point. The cosmic inventory is also a sequence of eras. Radiation dominated first. Photons and relativistic particles controlled the expansion. Matter later dominated, allowing structure to grow efficiently. Dark energy became dominant only recently in cosmic terms. Ordinary matter, dark matter, radiation, neutrinos, and dark energy all scale differently as the universe expands. The percentages we quote today are not timeless shares. They describe the present energy budget within the model. That is one of the most useful corrections to the simple pie chart. The pie changes with time. At recombination, dark energy was negligible in the standard model. Matter and radiation mattered most. In the far future, if lambda remains constant, matter will become increasingly diluted relative to dark energy. In the present era, we live after dark energy has begun to dominate, but while the evidence of earlier eras is still visible. Cosmology is possible because records from different epochs overlap. The CMB records the early universe. Light elements record the first minutes. Galaxy abundances and clustering record structure growth. Supernovae and BAO record expansion history. Weak lensing records mass distribution. Each record is incomplete alone. Together, they are enough to build a working inventory. I save the cartography state and step into the small side alcove where the lab stores old survey plates, mostly as a concession to sentiment. The plates are not originals, just high-quality reproductions, but they carry the feeling of older astronomy. Black fields, white stars, galaxies like thumbprints. The contrast with DESI's millions of redshifts is almost comic. Yet the old plates and modern catalogues share the same impulse. Record the sky carefully enough that it can surprise you later. Dark matter surprised astronomy by making visible galaxies too light. Dark energy surprised cosmology by making expansion too fast at late times. Missing baryons surprised us by making ordinary matter harder to find than expected. The CMB surprised us by being almost smooth, but not quite, carrying the seeds of everything that followed. The universe is generous with evidence, but not with simplicity. I leave the cartography lab and carry the file towards the sensor bay. The ship's night lighting has shifted to a faint blue along the lower panels. Through the portside viewports, a few stars show diffraction spikes from the glass layers. The sensor bay sits near the forward instrument cluster, behind a door with more locks than the galley and less charm. Inside, the room is cool. Screens show particle counts, radiation backgrounds, calibration pulses, detector temperatures, and instrument health. This is where the ship listens for things that are not visible through the dome. It is also the right place to talk about direct detection and the long patience of experiments that have not yet found what they were built to catch. Dark matter direct detection searches usually look for rare interactions between dark matter particles and ordinary matter in a detector. If a dark matter particle passes through Earth, it might occasionally scatter off an atomic nucleus, producing a tiny recoil. To see such a signal, experiments are built deep underground to reduce cosmic ray backgrounds. They use ultra-pure materials, shielding, cryogenic systems, liquid xenon or argon, germanium crystals, and careful event discrimination. The expected rate may be extremely low. Backgrounds can imitate signals. Every claimed hint must survive a hard accounting. So far, no direct detection has been confirmed. That statement should be plain. The null results are scientifically valuable. They rule out or constrain dark matter models with certain masses and interaction strengths. They push theorists away from simple regions and toward broader possibilities. The absence of a signal is still information. Indirect detection looks elsewhere. If dark matter particles annihilate or decay, they might produce gamma rays, neutrinos, positrons, antiprotons, or other particles. Searches examine the galactic center, dwarf spheroidal galaxies, galaxy clusters, cosmic rays, and diffuse backgrounds. Each target has complications. Astrophysical sources can mimic or hide signals. Cosmic rays propagate through magnetic fields. The galactic center is crowded and messy. Dwarf galaxies are cleaner in some ways, but faint. Collider searches bring the question into particle accelerators. If dark matter is connected to particles producible in high-energy collisions, detectors might see missing energy and momentum when invisible particles escape. But collider results depend on the interaction model. A missing energy event is not automatically dark matter. It must be interpreted through a theory connecting the collider to cosmological abundance and astrophysical constraints. Axion searches have their own methods. Some experiments use strong magnetic fields to convert axions into photons under resonant conditions. Others search for axion-like effects in precision measurements, astrophysical observations, or solar axion conversion. The parameter space is wide. The techniques are specialized. The search is a reminder that dark matter may not resemble the classic heavy particle many people first learn about. I stand in front of a detector status panel and watch a calibration pulse move across the screen. A detector is a disciplined form of hope. It is built around the possibility that the universe will interact with it in a measurable way, but it must be equally prepared for silence. In dark matter physics, silence has lasted a long time. The gravitational case grows stronger, the laboratory case remains open, and the space between them is where much of the work lives. I make a note on the page: do not oversolve the unsolved part. The same rule applies to dark energy. Describe the evidence, describe lambda, describe the cosmological constant problem. Mention dynamical dark energy and modified gravity as live possibilities. Treat DESI's hints as important but provisional. Leave the case open where the science leaves it open. The sensor bay door seals behind me as I step back into the corridor. Ahead, the ship opens toward the observation dome again. I can see a line of starlight on the floor where the dome's lower glass spills into the hall. The episode began in the office with a folder. It has moved through environmental systems, navigation, engineering, cartography, and sensors. The ship itself has become a way of sorting the categories: matter handled in life support, gravity handled in navigation, energy handled in engineering, geometry handled in cartography, detection handled in sensors. Now, the pieces need to come back together. I return to the office and spread the pages across the desk. CMB, BBN, baryon census, rotation curves, clusters, bullet cluster, candidate particles, supernovae, lambda, BAO, DES, DESI, weak lensing, structure growth. Each page is a partial witness. None is the whole sky. The office window shows the same darkness as before, but the file has changed the way it looks. The dark between stars is no longer a blank. It contains microwave photons from the early universe, neutrinos, thin plasma, interstellar dust, dark matter in the galactic halo, gravitational fields, and the expansion of space. Some of those things can be detected directly. Some are inferred, some are modelled. Some remain unknown in their physical nature. The word empty has become too simple. I draw 3 columns on the blank page: ordinary matter, dark energy. Under ordinary matter, I write atoms, ions, baryons, and electrons, stars, gas, dust, planets, plasma, intergalactic medium, light elements, chemistry. Under dark matter, I write gravitational mass, halos, structure growth, lensing, non-baryonic, particle unknown. Under dark energy, I write acceleration, lambda, negative pressure, expansion history, cosmological constant problem, possible evolution. The columns help, but they also mislead. The universe does not keep them as separate office folders. Ordinary matter falls into dark matter potentials. Dark energy changes the expansion background in which structure grows. Radiation reveals the early conditions. Neutrinos contribute subtly to the energy density and structure formation. Black holes form from ordinary matter, yet curve space-time intensely. Everything belongs to one system. Still, folders are how a mind works through a case. I sit with the page for a while, pen still in hand, the ship moving through a region of space where the star density on the forward display has begun to thin. The first version of the cosmic inventory most people hear is the present-day breakdown. Ordinary matter is a small fraction. Dark matter is larger. Dark energy is larger still. That version is useful, but it can make the universe sound static, as though the same percentages have always held and always will. The real story is more dynamic. Radiation once dominated the expansion. Matter later took command. Dark energy became dominant only in the relatively recent cosmic past. A present-day pie chart is a snapshot of a changing balance. I pull up a time display on the desk screen. It runs from the hot early universe to the present, compressed into a strip of light. At the left edge, the universe is dense, hot, and radiation-filled. Photons, electrons, positrons, neutrinos, protons, neutrons, and other particles are part of a thermal history no ordinary object could survive. The categories we use today existed in different forms then. There were no atoms at first, no stars, no galaxies, no planets. The universe had ingredients, but not the structures that make those ingredients visible. Radiation dominated early because relativistic particles carried most of the energy density. As the universe expanded, radiation diluted, and each photon lost energy as its wavelength stretched. Matter diluted too, but more slowly. At a certain point, matter became more important than radiation for the expansion. This matter-radiation equality is a key moment in structure formation. After it, gravitational growth of matter, perturbations became more efficient. Before recombination, ordinary matter was coupled to radiation. Electrons scattered photons, baryons felt radiation pressure. Dark matter in the standard picture did not scatter photons and could begin forming gravitational wells earlier. When the universe cooled enough for neutral atoms to form, the photons streamed away as the cosmic microwave background, and ordinary matter could fall more freely into the gravitational structure already taking shape. The first atoms were simple, mostly hydrogen, some helium, tiny amounts of other light nuclei. Heavy elements had to wait for stars. The first stars formed when gas collapsed in dark matter halos, cooled, and reached conditions for nuclear fusion. Their light ended the cosmic dark ages in patches. Their deaths began enriching the universe with heavier elements. Galaxies assembled hierarchically, through accretion and mergers shaped by dark matter halos and baryonic physics. Black holes grew, clusters formed at the knots of the web. Dark energy, if it is lambda, was present throughout as a constant density, but for most of early cosmic history it was dynamically negligible. Matter and radiation were denser then. Over time, matter thinned. Radiation thinned faster. Lambda did not thin. Eventually, its relative importance grew until it began to dominate the expansion. The acceleration inferred from supernovae belongs to this late chapter. The ship's screen shows the transition cleanly: radiation, matter, dark energy. 3 regimes, each with its own effect on expansion and structure. A simple line plot can make this look inevitable. It was not inevitable to the people measuring it. It had to be discovered through mismatches between expectation and observation. I close the time display and stand. The office feels too small for this part of the file, so I gather the folder and head toward the bridge. The bridge is 1 deck above the office, forward and slightly higher, set beneath a wider arc of glass. It is not as dramatic as old fiction would have it. No grand captain's chair, no unnecessary railings, no theatrical blinking consoles. The room is practical. 3 stations, a central navigation display, a panoramic forward window, and a standing console where long routes can be planned without sitting still. The ship mostly flies itself between decisions, but the bridge remains the place where all systems are gathered into one view. That is what Lambda CDM does for cosmology. It gathers different observations into one working model. The model assumes a homogeneous and isotropic universe on large scales, governed by general relativity, with a nearly flat spatial geometry, ordinary matter, cold dark matter, radiation, neutrinos, and a cosmological constant. It begins with early density fluctuations, often understood in the context of inflation, and follows their growth into the structures observed today. The base model has only a small set of main parameters: the baryon density, the cold dark matter density, the angular scale of the acoustic peaks, the amplitude and tilt of the primordial fluctuation spectrum, the optical depth associated with rayonization. From those, under the model assumptions, one can infer quantities such as the Hubble constant, matter density fraction, dark energy density fraction, and the age of the universe. It is a compact model for such a large subject. Its success can be stated without decoration. It fits the cosmic microwave background power spectrum. It predicts a baryon density consistent with Big Bang nucleosynthesis. It accounts for the broad growth of large-scale structure. It explains why galaxies and clusters require more gravitating matter than baryons provide. It accommodates the accelerating expansion through lambda. It agrees with BAO distances in a way that strongly supports the same underlying geometry. It is not complete physics, it is a successful cosmological model. I bring the bridge display online and ask for a base model parameter board. Values appear in a sober column: baryon density, cold dark matter density, Hubble constant as inferred by Planck under lambda c dm, optical depth, scalar spectral index. The display does not show wonder, which is its charm. It shows constraints, uncertainties, and model dependence. Model dependence matters. When Planck quotes a Hubble constant inferred from the CMB, that number comes through the assumed cosmological model. It is not the same kind of measurement as a local distance ladder using Cepheids and supernovae. Both are legitimate. They disagree more than their quoted uncertainties would lead one to expect. This is the Hubble tension. It may indicate unknown systematics in one or more measurements. It may indicate new physics. It has not yet been resolved. The cosmic inventory does not need a full Hubble tension file tonight, but the tension belongs in the room because it shows where the model is under pressure. If early universe inference gives one expansion rate today, and local distance measurements give a higher one, cosmologists must ask whether the assumptions connecting early and late universe are incomplete, or whether the measurements have hidden issues. Proposed solutions include early dark energy, extra relativistic species, modified gravity, calibration revisions, and other models. None has become the accepted fix. Another tension involves structure growth, often discussed through S8. Planck's early universe fit under lambda c dm predicts a certain amplitude of matter clustering today. Some weak lensing surveys and galaxy clustering analyses prefer a somewhat lower amplitude. The disagreement is milder than the Hubble tension, but it points in an interesting direction because it concerns the growth of structure, where dark matter, dark energy, neutrinos, and gravity all play roles. Again, systematics may be involved. Weak lensing is hard, galaxy bias is hard, photometric redshifts are hard. The tension is a clue under examination, not a conclusion. The bridge display rotates from parameter table to system diagram. Each observation connects to the model by a line. CMB to early parameters, BBN to baryon density, BAO to distance scale, supernovae to luminosity distance, weak lensing to structure growth, clusters to mass function, redshift space distortions to growth rate. The diagram looks like a circuit, which feels appropriate on a ship. A wrong component sends a fault through the system. A good model lets current pass through many paths. I rest both hands on the standing console. Outside the forward glass, the stars are fewer now. The ship has angled above a dust lane, and the galactic band lies lower in the field. A dark region cuts through it, not empty but obscuring. Dust hides light. Dark matter bends light. Dark energy changes distances. Darkness has several meanings in one sky. The name dark energy deserves another pass because it is easily turned into the wrong image. The cosmological constant does not behave like a gas in the engineering gallery. It does not clump around galaxies. It does not shine or cast shadows. It is represented as a uniform energy density with negative pressure. Within the Friedmann equations, that component causes accelerated expansion when it dominates. The name is a handle for a gravitational effect in the cosmological model. If dark energy is truly lambda, its equation of state is exactly W equals -1. If it evolves, W may differ from -1 and change with time. Observational programs try to measure this through expansion history and structure growth. Supernovae, BAO, weak lensing, clusters, and CMB data each contribute. The task is difficult because departures from lambda may be small, correlated with other parameters, or obscured by systematics. A result that looks like evolving dark energy must survive cross-checks before it becomes a new standard model. DESI's recent results are a good example of the discipline required. BAO data alone provide precise distance measurements. When combined with CMB and supernova data, certain model extensions allow a better fit with evolving dark energy. Some combinations show stronger preference than earlier analyses. Yet the interpretation depends on which supernova compilation is used and how systematics are handled. The right tone is neither dismissal nor celebration. The right tone is attention. The bridge keeps the whole ship in one view, so I stay there for the neutrino page. Neutrinos are not one of the headline categories in the title, but they belong in the inventory. They are real particles, extremely light, electrically neutral, and abundant. They were produced in the early universe and still contribute to the cosmic energy density. Because they move fast, they affect structure formation by suppressing small-scale clustering. Cosmology can place constraints on the sum of neutrino masses, complementing laboratory experiments. Neutrinos complicate the simple three-part story, and that is good. A public-facing case file can center on ordinary matter, and dark energy, while briefly acknowledging radiation and neutrinos. The universe is not literally only 3 ingredients. Photons matter, especially early. Neutrinos matter. Black holes matter locally and astrophysically, though they do not dominate the cosmic energy budget. The 3 headline components describe the dominant present-day accounting in the standard model, not every physical entity. The CMB also constrains the effective number of relativistic species, often called N-effective. In the standard model, this value is close to 3, with a correction from neutrino physics. Extra light relic particles would change the radiation density in the early universe and leave signatures in the CMB and Big Bang nucleosynthesis. This is another way the cosmic inventory reaches into particle physics. I shift the display to show particle species across cosmic time. Photons decouple at recombination and become the CMB. Neutrinos decouple much earlier, leaving a cosmic neutrino background that has not been directly detected in the same way as the CMB. Baryons form nuclei and later atoms. Dark matter freezes out, misaligns, forms, or otherwise acquires its relic abundance depending on what it is. Dark energy remains mysterious in origin. The early universe becomes a particle laboratory at energies far beyond daily life, but the laboratory is reconstructed from relics. There is a useful humility in that. Cosmology does not repeat the Big Bang in a chamber. It observes what survived. Photons, light element abundances, large-scale structure, backgrounds, distances. The universe ran the experiment once, everywhere, and the data arrive mixed with foregrounds, dust, calibration, gravitational evolution, and human analysis. The fact that a coherent model emerges at all is extraordinary enough without exaggeration. I leave the bridge and take the forward stairs down toward the archive again, this time stopping at a small alcove lined with mission patches, old photographs, and printed spectra. The alcove is a transitional space, not a room, but I like it. It holds evidence that does not need a full display: a spectrum of a quasar, an old CMB map, a galaxy cluster image, a supernova light curve, a BAO correlation function printed in black and white. Each is a different language. The supernova light curve shows brightness rising and falling over time. The CMB map shows temperature differences across the whole sky. The BAO plot shows a bump in galaxy clustering at a characteristic scale. The lensing map shows mass through distortion. The baryon census shows absorption lines. The dark matter candidate chart shows exclusions and allowed regions. None of these resembles the everyday act of counting objects in a box. The universe is counted by its effects. Normal matter can often be counted by light because it emits, absorbs, and scatters photons. Dark matter is counted by gravity. Dark energy is counted by expansion. Radiation is counted by background photons. Neutrinos are counted partly through their influence on expansion and structure. The method depends on the component. That is why the confidence levels differ. Ordinary matter is understood in the laboratory. Dark matter is gravitationally established but unidentified. Dark energy is cosmologically inferred but physically unresolved. A clean file should preserve those differences. It should not flatten them into equal mysteries. Ordinary matter is not mysterious in the same way as dark matter. Dark matter is not mysterious in the same way as dark energy. Dark energy is not dark matter wearing a different costume. The names are historical neighbours, not twins. I continue down the corridor to the archive and open a drawer marked Alternative Explanations. This drawer is not a threat to the main file. It is part of the main file. A scientific model earns trust not by avoiding alternatives, but by meeting them. Modified Newtonian dynamics and related theories address galaxy rotation in ways that reveal real regularities between baryonic matter and acceleration. Relativistic modified gravity theories try to extend such ideas to lensing and cosmology. Some models can handle parts of the evidence. The standard dark matter picture remains favoured because it fits more of the full cosmological dataset. For dark energy, alternatives include dynamical fields, modified gravity, inhomogeneous cosmologies, interacting dark sectors, and early dark energy models. Each comes with predictions and constraints. If dark energy evolves, BAO and supernova distances should reveal it. If gravity changes, structure growth and lensing should respond. If early dark energy helps the Hubble tension, it must also fit the CMB damping tail, BAO, and large-scale structure. Theories are not judged by charm. They are judged by survival. I close the drawer. Too many alternatives can blur the central thread. Still, mentioning them prevents the listener from thinking cosmologists simply named the unknown and stopped. Naming is the beginning of the hard part. Dark matter and dark energy are placeholders with evidence behind them and questions inside them. The ship's intercom gives a soft chime, not an alarm, just a course update. A minor rotation will begin in 30 seconds to keep the forward shield aligned with the local dust flow. I feel it as a slow change in balance, almost below perception. The stars in the long viewport shift. The ship is moving through ordinary matter, thin as it is, and even thin matter matters at speed. This is a useful bridge back to baryons. Ordinary matter has interactions. It collides, it heats, it cools, it shocks. It forms disks because it can radiate energy away. Dark matter, lacking strong electromagnetic interactions, does not collapse into thin disks the same way. It forms extended halos. That difference explains why galaxies have bright disks embedded in larger dark halos. Baryons can lose energy and settle. Dark matter keeps a puffier distribution. The same difference appears in cluster collisions. Gas collides and slows. Dark matter passes through if it is effectively collisionless. The bullet cluster's separation between gas and lensing mass constrains dark matter self-interactions. If dark matter interacted strongly with itself, it might lag or spread differently during the collision. Observations of cluster mergers therefore do more than show dark matter's existence. They also constrain its properties. I add a note to the dark matter page. Darkness is a behaviour, not merely absence. Dark matter is dark because it does not interact electromagnetically in the ordinary way, but it is not inactive. It gravitates, it clusters, it shapes potentials. It may self-interact weakly or not at all. It may have a dark sector. The evidence we have is strong for its gravitational role and weak for its non-gravitational personality. In a human room, ordinary matter dominates experience. In a galaxy, dark matter dominates much of the mass. In the universe's present energy budget, dark energy dominates the expansion dynamics. Different scales reveal different rulers of behaviour. The same cup of tea that feels substantial in my hand is negligible in a galactic halo. The same dark matter halo that shapes a galaxy is less important than dark energy for the fate of sufficiently large unbound distances. I return to the office with that scale in mind. The desk has become crowded enough that I begin sorting pages into 3 stacks. Ordinary matter on the left, dark matter in the middle, dark energy on the right. A 4th, smaller stack sits above them, radiation and neutrinos. The old cosmic background page belongs partly there, partly everywhere. The CMB is radiation now, but it is also a map of matter then. It tells us about baryons and dark matter through acoustic peaks. It tells us about geometry through the angular scale. It tells us about rayonization through polarization. It tells us about lensing through the smoothing and reconstruction caused by intervening matter. One observation can touch many parts of the inventory. The same is true of BAO. It is a feature caused by baryon photon physics, visible in galaxy clustering shaped mostly by dark matter, used to measure dark energy through expansion history. One phenomenon crosses all 3 headline categories. The universe does not respect our chapter breaks. I take a fresh sheet and write. The cosmic recipe is measured by relationships, baryons to photons, matter to radiation, dark matter to baryons, expansion to distance, geometry to acoustic scale, lensing to mass, growth to time. Each relationship narrows the possible universe. The model that survives must satisfy all of them at once. The office lights dim slightly as the ship's night cycle deepens. I can hear the reactor hum through the deck now, or perhaps I am only noticing it because engineering is still in mind. The folder has begun to feel less like a case file and more like a ship's system diagram. Remove one component and the rest no longer behave correctly. If there were no dark matter, the CMB peaks would change, structure formation would struggle, clusters would weigh too much, lensing maps would fail, and galaxy rotation curves would need a different explanation across many scales. If there were no dark energy in a flat universe with the measured matter density, supernovae would sit wrong on the distance redshift diagram, BAO distances would shift, and the inferred age and geometry would conflict. If there were far more baryons, Big Bang nucleosynthesis and CMB acoustic peaks would object. If there were far fewer, stars and gas and light element abundances would object. That is how the inventory holds together. Not because every piece is understood, but because the pieces have to fit the measurements. The next page is the one where all three main components meet in the early universe's acoustic pattern. I pull the Planck sheet forward again and study the peaks. The first peak tells geometry and overall scale. The relative peak heights carry baryon and dark matter information. The damping tail carries information about diffusion and relativistic species. Lensing of the CMB carries information about intervening structure. A single curve encodes a universe. The plasma before recombination supported waves. Gravity compressed, radiation pressure resisted. Baryons added inertia. Dark matter shaped gravitational potentials. Different wavelengths were caught at different phases when photons decoupled. The pattern became the CMB anisotropy spectrum. By fitting that spectrum, cosmologists infer the composition of the universe. The acoustic peaks are not like sound in air now. No one would hear them. The early universe was dense and hot, and the waves were fluctuations in a coupled plasma. The word sound is a physical analogy with real meaning, because pressure waves travelled through the medium. But the scale was enormous, and the conditions alien. The fossil of that sound is not a note. It is a statistical pattern in microwave temperature and polarization. The BAO feature is the same early physics echoed later in matter clustering. That link gives cosmology a long baseline across time. The same early sound horizon appearing in two different records, the CMB and the galaxy distribution. I file the Planck sheet behind the timeline and stand again. The ship has one more room for this part of the case, the lower observation well. The well is not a dome. It is a downward-facing viewport beneath the forward decks, used mostly for close inspection of planetary surfaces, debris fields, or docking structures. Tonight, it shows only stars, because there is no up or down in interstellar space unless the ship assigns one. The room is small, circular, and dim, with a ring bench around the glass. I sit with the folder beside me and look down into the universe. Looking down at stars is a good way to loosen Earth habits. The mind expects sky above and ground below. In the well, sky is below too. Matter, and dark energy have no respect for human orientation. They operate in every direction. The cosmic microwave background surrounds us. Galaxy surveys look outward along a past light cone. Expansion has no center in space. Every observer in the homogeneous universe sees distant galaxies receding on average. This matters because the Big Bang was not an explosion into empty space. It was the hot, dense state of space itself, followed by expansion. The observable universe is the region from which light has had time to reach us since the beginning. Beyond it may be more universe, perhaps vastly more, but not observable by us now. The cosmic inventory refers to the observable universe and to the model extending beyond it under the assumption of large-scale homogeneity. In the observation well, the glass reflects the folder faintly. Ordinary matter in my hand, dark matter in the galaxy, dark energy in the equations of expansion, radiation from the early universe passing through the ship, neutrinos passing through almost everything. The categories overlap in the same room without touching in the same way. A person walks through ordinary matter, navigates by gravity, studies energy systems, maps galaxies, checks detectors, and returns to the desk with a file that remains open. I close the folder for the moment and watch the stars below. The model has gathered itself. Lambda, CDM, cosmic eras, radiation, neutrinos, tensions, systematics, and relationships that make the inventory more than 3 numbers. The listener has the evidence now. What remains is to let the evidence settle into scale. I stay in the lower observation well longer than I planned. The glass beneath my feet shows a field of stars without horizon, and the body keeps making small corrections it does not need to make. It wants a floor, it wants a ceiling, it wants the old arrangement. Ground below, sky above, weight pointing one way. A ship can imitate that arrangement with rotation or acceleration, but the universe outside does not share the habit. There is no preferred up in the cosmic inventory. The microwave background arrives from every direction. Dark matter surrounds the galaxy in a halo that does not care where a deck begins. Dark energy, if lambda is the right description, is not piled in one place more than another. It is part of the large-scale accounting of space itself. The categories on the page are human categories, useful ones, but human. Ordinary matter, dark energy, radiation, neutrinos, curvature, parameters. They are ways of describing what the universe does when averaged over scales large enough that individual stars and galaxies become details. A person can hold ordinary matter in one hand. A person cannot hold a dark matter halo, or a cosmological constant, or a sound horizon from the early plasma. Still, the evidence reaches the hand eventually. It reaches the detector built from atoms. It reaches the mirror. It reaches the chip. It reaches the notebook. I gather the folder and climb back towards the forward decks. The ship is beginning to brighten into its artificial morning. The change is slight. A little more white in the corridor lights, a little less amber near the floor. No sun rises. The schedule changes because people work better when time has shape. Cosmology does something similar with eras. Radiation domination, matter domination, dark energy domination. The divisions are not walls in time. They are changes in which component controls the expansion most strongly. The first stop is the materials alcove beside the workshop. It is a narrow room with sample drawers, repair stock, spare seals, ceramic tiles, composite patches, wiring harnesses, and labelled containers of powdered alloys. It smells faintly of machine oil and plastic, despite the filters. I open one drawer and take out a small square of hull plating, no larger than my palm. It is layered. Micrometeoroid shielding, thermal control surface, structural composite, conductive mesh. Ordinary matter arranged with intention. This is the easiest part of the universe to overtrust. Ordinary matter is tangible, so the mind gives it priority. We know its forces well. Electromagnetism gives atoms their structure and chemistry. The strong force holds nuclei together. The weak force governs certain radioactive processes and nuclear transformations. Gravity gives ordinary matter weight and gathers it at large scales. The standard model of particle physics describes much of this behaviour with precision that would have seemed impossible a century ago. Yet ordinary matter occupies only a narrow share of the present cosmic energy budget. That does not make it incidental. It makes it special in a different way. Ordinary matter cools. It radiates. It forms disks, stars, planets, minerals, oceans, organic chemistry detectors, and questions. It is not dominant by mass energy, but it is complex. Dark matter dominates the mass in galaxies and clusters, but it does not make atoms in the ordinary sense. Dark energy dominates the current expansion, but it does not make structures. Complexity is not proportional to cosmic abundance. The workshop bench has a microscope built into it for inspecting microfractures in replacement parts. I slide a bit of dust from a sealed sample under the lens. On the screen, the speck becomes jagged, irregular, mineral. Dust is one of ordinary matter's quieter forms, but in astronomy it matters constantly. Dust dims and reddens starlight. It complicates supernova cosmology. It glows in infrared. It forms in stellar outflows and supernova ejecta. It helps molecular clouds cool and form stars. It becomes part of planets. It can both obscure evidence and become evidence. When supernova teams measured cosmic acceleration, dust was one of the obvious concerns. If distant supernovae looked fainter, perhaps intervening dust made them appear that way. Ordinary dust reddens light, changing colour as well as brightness. More exotic grey dust was considered as a possible contaminant. The teams investigated such alternatives. Later observations across larger redshift ranges and independent probes strengthened the acceleration case. This is a useful reminder that ordinary matter can masquerade as cosmology if its effects are not controlled. The same is true in the CMB. Foreground emission from our galaxy must be modelled and removed. Dust, synchrotron radiation, free emission, point sources, and other foregrounds stand between us and the early universe. A clean CMB map is not a raw photograph of creation. It is the result of instruments, frequency channels, calibration, masks, component separation, and analysis. That does not weaken the result. It explains the work required to make the result trustworthy. I return the dust sample and close the drawer. The file now has a margin note beside ordinary matter, familiar, complex, sometimes obstructive. It is easy to think of ordinary matter only as the known part, but in observation it is often both signal and foreground. Gas traces baryons, dust hides supernovae, stars show galaxy structure but do not trace all mass. Plasma in clusters reveals baryons while separating from dark matter in mergers. Ordinary matter is not a passive 5%. It is active, luminous, collisional, chemically rich, and difficult. From the workshop, I walk aft toward the small stellar physics display built into the education console. No one on board needs it for operations. It is there because a ship with long corridors benefits from reminders of why its instruments exist. I load a simple stellar evolution sequence. A gas cloud collapses. A protostar forms. Fusion begins. A main sequence star shines. Later, depending on mass, it swells, sheds layers, explodes, leaves a white dwarf, neutron star, or black hole. Heavy elements are made and distributed. The question tonight is not where the elements come from, but the transformation matters. Baryons become chemistry through stars. Hydrogen and helium dominate the raw material. Stars process that material into heavier elements. Supernovae, stellar winds, and neutron star mergers seed galaxies with metals. Planets form from enriched gas and dust. The ordinary matter in the office is not primordial in its current form. It has been through generations of astrophysical processing. The cosmic inventory at the level of omega parameters does not care whether a baryon is in hydrogen gas or a carbon atom in a living cell. The baryon count is the baryon count. But for the file, the transformation matters. The 5% contains a history of increasing complexity. It begins as simple nuclei and later becomes the periodic table, not because the universe intended complexity, but because gravity and nuclear physics created stars, and stars altered the material available for the next generation. I close the stellar sequence and take the aft passage toward the Halo simulator. That name is informal. The room is actually a gravitational modelling suite used for plotting trajectories near complex mass distributions. But someone labelled the local display Halo during a maintenance update years ago, and the name stayed. The suite is circular and dark, with a central projection volume and a ring of hand controls. I load a Milky Way mass model. The luminous disk appears first, then the bulge, then the stellar halo, then the dark matter halo extending far beyond the bright edge. The scale has to adjust twice before the whole halo fits. The visible disk that seems so large in photographs becomes a bright inner feature inside a much larger mass distribution. Dark matter is often introduced through what it is not. It is not stars. It is not dust. It is not cold gas. It is not ordinary black holes in sufficient quantity. That negative introduction is useful for clearing confusion, but the positive role matters more. Dark matter forms gravitational structures. It seeds halos. It affects galaxy rotation. It bends light. It shapes the cosmic web. It supplies most of the matter density in lambda CDM. The Milky Way's dark halo is not directly visible, but its existence is inferred from several lines of evidence: the motion of stars and gas, the dynamics of satellite galaxies, stellar streams, the escape speed near the Sun, and broader cosmological modelling. The local dark matter density near the solar system matters for direct detection experiments. It is not known with perfect precision, and it depends on assumptions about the halo shape and dynamics. But it gives experiments a target: a flux of dark matter particles passing through Earth if the particle picture is right. I zoom into the solar neighbourhood. The Sun appears as a small marker orbiting the galactic centre, embedded in the disk and moving through the halo. The image is humbling in a technical way. The solar system is not outside the dark matter problem, looking in. It moves inside a dark matter distribution. Detectors on Earth, if sensitive to the right interaction, are carried through the halo by the Sun's galactic orbit and by Earth's motion around the Sun. Direct detection experiments often look for annual modulation, a seasonal change in event rate caused by Earth's changing velocity relative to the dark matter halo. A claimed modulation must be treated cautiously because backgrounds can vary seasonally too. The general idea, though, reveals something important. Dark matter is not only an astronomical inference at the edge of galaxies. If it is made of particles with even tiny interactions with ordinary matter, it may be passing through the laboratory every second. That closeness can be unsettling, but it is also precise. Dark matter is not a fog that can be felt, not a shadow in the room, not a substance pressing against skin. Its interaction with ordinary matter, if any, is so rare that enormous detectors and long exposures are needed. Gravity tells us it is there. Non-gravitational detection remains the missing step. The halo model rotates slowly. I add satellite galaxies, then globular clusters, then stellar streams. Streams are useful because they can reveal the gravitational potential through their orbits and disruptions. If dark matter halos contain substructure, streams may show gaps or perturbations. The galaxy becomes a laboratory for dark matter distribution. Not an easy laboratory because baryons complicate the potential, but a nearby one. Dark matter also shapes galaxies beyond the Milky Way. Dwarf galaxies are dark matter dominated, with high mass-to-light ratios. Galaxy clusters require enormous dark matter halos. Weak lensing across large surveys maps dark matter statistically. Strong lensing can reveal substructure through anomalies in multiple images. The same component appears from small galaxies to the cosmic web, though the details vary by scale. This is why the case is strong. It is not that every observation is simple. Many are not. Galaxy formation has small-scale challenges, core cusp questions, missing satellites, too big to fail issues, diversity in rotation curves. Baryonic feedback can change inner dark matter profiles by driving gas in and out. Star formation, Supernovae and black hole activity can reshape central regions. Some tensions may teach us about baryonic physics, some may point to dark matter properties. The standard model works best on large scales and remains actively tested on smaller ones. I close the Milky Way halo and load a cluster merger again, but not the bullet cluster this time. Other merging clusters also test dark matter self-interaction and mass-gas separation. The point is that bullet is not alone, though it is famous. Cluster mergers are laboratories where components separate according to interaction strength. They help constrain how collisional dark matter can be. If dark matter self-interacts too strongly, cluster collisions would look different. Observations put upper limits on that self-interaction cross-section, while some self-interacting models remain possible at lower levels. The display shows gas in one layer, galaxies in another, lensing mass in a third. I think again of the ship. Air in ducts, coolant in pipes, crew in corridors, radiation through shielding, gravity through everything. Components reveal themselves by how they respond to conditions. The universe is the same, only larger and less forgiving. I leave the modelling suite and head towards the long central corridor. The corridor runs nearly the full length of the ship. On one side are workrooms and storage lockers. On the other are viewports spaced at regular intervals. I walk without opening the file. Sometimes a case needs less reading and more distance. The next component, dark energy, is harder to picture because it does not gather into a halo or leave absorption lines. Its evidence is the expansion history and the growth of structure. It is measured by geometry more than by presence. The supernovae told us the expansion is accelerating. BAO measures distances and expansion rates. The CMB anchors the early universe and constrains the geometry. Weak lensing and clustering show how structure grows under the combined influence of matter and dark energy. If lambda is correct, the future is mathematically simple in outline. The universe keeps expanding at an accelerating rate. Matter becomes more diluted. Star formation eventually declines as gas is used up or heated. Existing stars age and die. Gravitationally bound systems, such as the local group, remain bound, but distant unbound galaxies recede beyond practical observation. The cosmic microwave background cools further. The universe tends toward a colder, darker state. This does not need to become a doom section. The timescales are enormous. The point is not to frighten, it is to show that the ingredient list affects the future. Matter tries to pull. Dark energy accelerates the expansion. The balance determines cosmic fate. Before dark energy, cosmologists debated recollapse versus endless slowing expansion in terms of matter density and curvature. With dark energy, the future depends on the nature of that component. A cosmological constant leads one kind of future. Evolving dark energy could lead others. If dark energy grows stronger with time in certain phantom models, more extreme futures become possible, including a big rip. Current observations do not require such a fate, and it would be a mistake to make it central here. If dark energy decays or changes sign in some models, the future could differ sharply. But these are speculative branches. The evidence-supported baseline remains lambda CDM, with acceleration continuing. I stop at a viewport and look out. The star field is thinner here, the ship angled away from the densest part of the Milky Way. A few stars are bright enough to show colour. Most are faint and white. Between them, black. The darkness looks like absence because human eyes are tuned to light. But the file has trained the eye differently. Between stars, there is matter, radiation, gravity, expansion, and history. The cosmic microwave background is everywhere in that darkness. Its photons pass through the ship from all directions, though the hull and instruments interact with only a fraction in any useful way. Relic neutrinos are there too, harder still to detect. Dark matter from the galactic halo may be passing through. Interstellar gas and dust lie thinly along the path. Dark energy, if lambda, is not in the darkness like a mist. It is part of the large-scale dynamics that make the distances between unbound galaxies grow faster over time. The word nothing becomes hard to use after cosmology. A region can be empty of stars and still contain fields, particles, backgrounds, and geometry. Even a perfect vacuum in quantum field theory is not simple nothing. But the hard science lane is wide enough. Measured backgrounds, inferred components, expansion history. I continue walking. The corridor curves slightly near the forward shielding. A maintenance panel is open, revealing bundled cables labelled by system. Navigation, thermal, comms, external sensors, life support. A ship is easier than a universe because someone labelled the cables. Cosmology labels components after measuring what they do. Sometimes the label is provisional, dark matter, dark energy. The names admit the gap. That admission is important. Scientists did not call dark matter dark because they understood it. They called it dark because the gravitating mass was not emitting light. Dark energy was named because something like an energy component seemed to be driving acceleration, though its physical nature was unknown. The names are honest in their incompleteness. They are not explanations by themselves. I return to the office. The lamp has timed itself down to a softer setting, and the desk screen has gone blank. I wake it and open the integrated timeline again. The first few minutes glow at the far left. The CMB marker sits later, still early by cosmic standards. The formation of the first stars appears as a small region after the Dark Ages. Galaxies grow, clusters form, heavy elements build, planets appear, observers arrive late. The present-day composition sits near the right edge. Ordinary matter, dark energy. The screen can show the numbers, but I leave them hidden for now. The story works better before the numbers return. We have followed the evidence. The numbers should now feel like a result, not a slogan. When I finally bring them up, they appear without fanfare. Roughly 5% ordinary matter, roughly a quarter to a little more in dark matter, roughly 2/3 to dark energy. The exact values depend on dataset and model, and public versions are rounded. The Planck lambda CDM numbers are more precise than the rounded story. But for narration, the rounded figures are enough if the caveat is clear. The ordinary matter fraction is not the same as the matter fraction. Total matter includes ordinary and dark matter. Matter as a whole is about 30% of the present energy density in the standard model, with dark energy around 70%. Radiation is tiny today, though it dominated early. Neutrinos contribute a small amount depending on mass. Curvature is constrained close to zero. This is the present cosmic budget. I write the numbers on the page and then write below them. Today, under lambda CDM. That phrase belongs in the file. Today, because the fractions evolve. Under lambda CDM, because the values are model-based constraints within a successful framework. Not uncertain in the casual sense, but not detached from assumptions either. Precision cosmology is precise because it is explicit about its model. Ordinary matter is known in the laboratory and counted cosmologically through the CMB, light elements, and astrophysical surveys. Dark matter is weighed through gravity and structure. Dark energy is inferred through distances, expansion, and growth. The ship's office is almost fully lit now. Artificial morning has arrived, though the stars outside remain unchanged. The folder has grown heavier with pages, and I begin arranging the final notes. The universe is not made mostly of stars. Stars are a visible minority of a minority. Ordinary matter itself is spread through many phases, much of it outside stars. Dark matter is required by multiple gravitational lines of evidence and by the success of structure formation in the Standard Model. Dark energy names the late-time acceleration component, with lambda as the simplest and still baseline explanation. The frontiers are real: dark matter detection, dark energy evolution, Hubble tension, S8 tension, missing baryons, neutrino masses, and the cosmological constant problem. I stand and take the folder back towards the observation dome, where the case first opened beyond the desk. The corridor is brighter now. The maintenance drone that was docked earlier has moved. Only its charging contact remains, a small dark square in the wall. Somewhere below, the environmental system shifts airflow. The ship is awake. In the dome, the galaxy is still there. It has rotated slightly in the window because the ship has changed attitude. The Milky Way band lies diagonally now, dust lanes cutting through star fields. It looks like a thing made of light until one remembers the dark matter halo surrounding it, the gas between its stars, the dust hiding parts of it, the black holes in its history, the dark energy shaping the space beyond its bound region. A galaxy is not a simple luminous island. It is a concentration of matter inside a larger gravitational context. Its stars tell one part of the story. Its gas tells another. Its motions tell another. Its satellites, streams, and halo tell another. Its place in the cosmic web tells another. The universe is made of components, but we encounter them as behavior. I set the folder on the dome console and open to the first page again. The cold open asked what had to be present for the measurements to agree. The answer is not merely 3 ingredients. It is an interlocking model supported by old light, nuclear chemistry, gravity, distance, and maps. A listener should come away with a better kind of uncertainty. Not the uncertainty of knowing nothing, but the uncertainty of knowing which parts are solid and which parts remain open. We know ordinary matter well, but not every baryon's location. We know dark matter's gravitational role, but not its identity. We know cosmic acceleration is real within the web of evidence, but not the deep physical reason behind lambda or dark energy. We know the Standard Model works exceptionally well, but we also know where it is being tested. I look out through the dome and imagine the cosmic microwave background behind every visible star, a surface of last scattering that does not sit behind the stars in ordinary distance so much as around the observable universe in every direction. The starlight is local by comparison. The CMB is ancient. The galaxy is middle-aged. Dark energy is late-time dominance. The file is not only spatial, it is temporal. The universe was once too hot for atoms. It made light nuclei. It became transparent. It formed structure. It accelerated. It is still expanding. The contents matter because they change how that history unfolds. I close the folder halfway and leave it on the console while I walk one last circuit around the dome. A ship's dome is a compromise, a window pretending to be openness. But it is enough. It lets the dark in without letting the vacuum in. It lets the eye practice scale from a safe room. The safe room is ordinary matter. The gravity holding the galaxy together is mostly dark matter. The expansion carrying unbound galaxies away is shaped by dark energy. The photons arriving from the early universe are radiation. The neutrinos pass through. Everything in the inventory is present in some way. even here, even in a small room on a fictional ship. I take the folder from the console and return to the office. The desk is clear now except for the lamp, the mug, and 3 pages placed side by side. Ordinary matter, dark energy. I leave space beneath each one for the final notes. Under ordinary matter, I write known, luminous and dark, chemically rich, partly hidden in diffuse gas. Under dark matter, I write gravitationally measured, structurally essential, particle unknown. Under dark energy, I write acceleration, lambda baseline, physical origin unknown. Then, beneath all 3, I write 1 sentence for the closing file. The universe is made not only of what we can see, but of what the evidence requires us to include. I leave that sentence on the page and do not underline it. It can stand without help. The office has settled into morning light now, the kind made by panels and schedules rather than a star. Outside the dome, nothing has brightened. The same dark field waits beyond the glass. The ship has turned enough that the Milky Way band has moved off-centre, and a quieter patch of sky fills the upper window. Fewer stars, more dark between them. A person could mistake that darkness for a lack of information. The file says otherwise. 3 pages sit in front of me. Ordinary matter, dark energy. The terms look almost balanced on paper, as if they were 3 neighbouring departments in the same building. They are not balanced in abundance, and they are not known in the same way. That is the final shape the episode needs to hold. The categories belong together because the universe requires all 3 in the standard model. They must be treated differently because the evidence for each travels by different routes. Ordinary matter is the matter of atoms and ions, the matter that interacts with light, the matter that makes chemistry possible. It is counted by the early universe through the acoustic peaks of the CMB and through Big Bang nucleosynthesis. It is counted in the nearby universe through stars, gas, plasma, absorption lines, X-rays, and surveys of galaxies and their surroundings. It is not all bright. It is not all easy. Some of it lies in warm, hot filaments and circumgalactic gas, difficult to see except by the marks it leaves on light from farther away. Dark matter gives fewer answers. It does not respond to light in the usual ways. It does not form atoms that emit spectra. It does not cool into bright disks. It does not announce itself in chemistry. It is weighed through gravity. Its presence is inferred through the motions of galaxies, the dynamics of clusters, gravitational lensing, the pattern of the cosmic microwave background, and the growth of large-scale structure. The evidence is strong because it comes from many scales and methods, but the identity of the dark matter remains unknown. I slide the dark matter page beside the first. On it are the names of possible candidates, some crossed out lightly, some circled, some left in the margin for later. WIMPs, axions, sterile neutrinos, primordial black holes, hidden sectors, self-interacting models, ultralight fields. The list is not a menu of equal options. Each possibility has its own motivations and constraints. The point for this case file is more basic. The universe behaves as though most matter is non-baryonic and dark, and the laboratory has not yet told us what that matter is. Dark energy is stranger still. I place its page on the right, leaving more blank space beneath it. It is the name given to the component, or effective component, responsible for the observed accelerated expansion of the universe. In the baseline model, it is lambda, the cosmological constant. Lambda fits a great deal of data. It is simple in the equations. It is hard in physics. If it represents vacuum energy, its measured value is far smaller than naive quantum estimates. If it represents something dynamical, The field and its behaviour must be explained. If it points to modified gravity, that theory must preserve the many successes of general relativity while changing the cosmic scale behaviour. The evidence for dark energy is not a single object. It is a pattern in distances, redshifts, geometry, and structure growth. Type 1, a supernovae revealed acceleration. BAO gives a standard ruler across cosmic time. The CMB anchors the early scale and geometry. Weak lensing and galaxy clustering test how structure grew under the influence of matter and dark energy. Modern surveys sharpen the question. DES, DESI, Euclid, Rubin, Roman, and other programs are not merely making prettier maps. They are asking whether lambda remains enough. The ship gives a small tone from the bridge. Not an alarm, only a navigation update. The next correction burn has been scheduled. I leave the pages on the desk and walk forward. It feels right to finish the case away from the desk with the ship in motion. The corridor is brighter now, and for the first time in the episode, it has the ordinary feel of a working morning. A panel is open near the floor where a repair system has left a diagnostic tag. The environmental bay hums below. The cartography lab is still awake from the last session, its door rim glowing faintly. The archive shelves are locked. The sensor bay remains cool and sealed. The whole ship has become a map of the file. I step onto the bridge as the correction sequence begins. The forward glass holds a sparse star field. The central display shows the maneuver in clean lines. Current vector, target vector, burn duration, fuel cost, expected drift. Navigation is a practical form of cosmology in miniature. The ship moves through space-time according to mass, velocity, gravity, and energy. The universe does the same without a pilot and without a destination. The burn starts gently. There is a slight pressure through the floor, enough for the body to notice. The stars do not visibly move. Instruments know the change before the eye does. That is a useful final lesson. The universe often changes first in the instruments. A supernova is a point of light until a light curve turns it into a distance. A galaxy image is a smudge until spectra turn it into redshift. A weakly distorted background galaxy is noise until millions of shapes become sheer. A microwave map is mottled colour until the power spectrum gives parameters. A sky full of galaxies is a picture until correlations reveal the acoustic scale. The evidence rarely arrives already translated. People translate it through theory, calibration, statistics, and repeated checks. That translation is not a weakness, it is the work. The bridge display shifts to the ship's wide-field external sensors. The dark sky becomes layered with information: star positions, dust estimates, radiation counts, local gravitational model, instrument background, predicted micrometeoroid flow. The view through the glass and the view through the sensors are not the same view. One is what the eye receives, the other is what the ship can measure. Cosmology lives mostly in the second kind of view. Still, the eye matters. It keeps the scale from becoming only numbers. The eye sees the darkness and asks what is there. The instruments answer in parts: microwave photons, thin gas, dust, gravitational fields, dark matter halos, expanding space. The answer is not one thing, it is a layered account. I return to the office for the final pages. The maneuver ends before I reach the door. The floor pressure relaxes. A status light on the corridor wall changes from amber to green. Inside the office, the 3 pages wait exactly where I left them. No page has solved itself in my absence. The ordinary matter page comes first. If someone asks what the universe is made of, ordinary matter is the part they already know how to imagine. but it should not be introduced as a minor afterthought. It includes every atom in every star and planet, every cloud of gas, every dust grain, every ocean, every organism, every detector. It is the matter of the periodic table, though the periodic table itself required stars to build most of its entries. Cosmologically, this matter is counted as baryons, plus the electrons needed for atoms and plasma. It is about 5% of the present cosmic energy budget in the Standard Model. The dark matter page comes second. It is not ordinary matter hidden in the dark. It is not merely a bookkeeping mistake created by unobserved planets or cold gas. The allowed amount of baryonic matter is too small, and the gravitational evidence extends too widely. Dark matter is inferred from galaxy rotation curves, cluster dynamics, gravitational lensing, CMB structure, large-scale structure, and cluster collisions where ordinary gas separates from the dominant inferred mass. It makes up most of the matter in the universe, though not most of the total present energy budget once dark energy is included. The dark energy page comes third. It should be introduced through expansion, not through a picture of substance. The universe is expanding, and the expansion is accelerating. Type 1, a supernovae, provided the discovery evidence. BAO-CMB, and large-scale structure support and refine the picture. In lambda CDM, dark energy is represented by the cosmological constant, with constant density and equation of state W equal to -1. This simple description fits current data well, though modern surveys continue to test it. Above the 3 pages, the smaller radiation and neutrino page belongs as a correction to the simple story. Today, radiation contributes very little to the total energy density, but in the early universe, it dominated. The CMB is radiation left from that era. Neutrinos are abundant and affect both the early expansion and the growth of structure. They are not the main focus of the title, but leaving them out completely would make the inventory too clean. The universe is allowed to be more complex than the thumbnail. I arrange the pages into a line that follows time. Radiation first, Big Bang nucleosynthesis, CMB, matter domination, structure formation, stars and galaxies, acceleration, present dark energy domination. The 3 headline ingredients now sit inside a temporal sequence, and the sequence feels more honest than the pie chart. The file's last scientific caution concerns the word evidence. Evidence in cosmology is not the same as direct handling. We do not hold a dark matter particle. We do not bottle dark energy. We do not travel to the last scattering surface. But direct handling is not the only standard for knowledge in astronomy. We know the cause of stars through light, neutrinos, oscillations, and theory. We know black holes through orbits, accretion, gravitational waves, and imaging. We know exoplanets through transits, radial velocities, direct imaging, microlensing, timing, and spectra. The universe often gives effects before it gives objects. Dark matter and dark energy should be judged with that in mind, but not with lowered standards. The standards are high. They require consistency, prediction, cross-checks, independent probes, and vulnerability to being wrong. Lambda CDM survives because it has passed many of those tests. It remains under examination because some questions are unresolved and some tensions are real. I add the final working note: strong model, open physics. Lambda CDM is a strong model. Dark matter and dark energy point to open physics. Ordinary matter is well understood locally, but cosmically dispersed in complex ways. Radiation and neutrinos complete the larger accounting. The next generation of surveys and experiments will not simply add details. They may identify the dark matter particle, confirm lambda more tightly, reveal dark energy evolution, resolve tensions, or uncover systematic errors in places that now seem solid. I think of Euclid mapping galaxy shapes and distances across a large fraction of the sky, Rubin Observatory scanning the changing sky, measuring weak lensing, supernovae, and structure. Roman adding space-based infrared surveys and supernova cosmology. DESI extending spectroscopic maps. CMB, Stage 4, aiming for sharper measurements of the early universe, lensing, neutrino properties, and primordial signals. Underground detectors growing quieter and more sensitive. Axion searches scanning patient ranges of possibility. Each project adds another instrument to the case. A future version of this episode may need different caveats. Perhaps dark matter will have a particle name. Perhaps DESI's hints will fade under new supernova calibrations or grow stronger with more data. Perhaps the Hubble tension will resolve into systematics or force a change in early universe physics. Perhaps weak lensing surveys will converge on Planck or deepen the S8 question. Science does not preserve scripts for our convenience, it revises them. For now, the careful answer stands. The universe is made, in the present standard cosmological model, of a small fraction of ordinary matter, a larger fraction of dark matter, and a dominant dark energy component. But those words compress a long chain of evidence. Ordinary matter is measured through atoms, light, nuclei, gas, and the microwave background. Dark matter is inferred through gravity, lensing, motion, and structure. Dark energy is inferred through acceleration, distances, geometry, and the growth of cosmic structure. Each category is a conclusion, not a guess placed over ignorance. I close the pen. The pages remain open. The office is fully lit now, but I dim the lamp back down by hand because the file began under warmer light and should end there. Outside, the forward dome holds the same dark that has been with us all along. A few faint stars mark the glass. Most of the view is black. When the file began, that blackness might have looked like empty background. Now it is full of qualifications. Some darkness is dust-blocking stars. Some is distance. Some is the absence of luminous matter. Some contains thin gas too faint to see. Some is threaded by dark matter's gravitational influence. Some is the expanding space between bound structures. Some carries microwave photons too cold for the eye. The eye calls it dark because the eye is not the right instrument. I gather the 3 main pages and place them back into the folder. Ordinary matter first, dark matter second, dark energy third. Then I add the smaller page on radiation and neutrinos behind them, because a good file should not hide the supporting cast. The folder is too thick now for its original clip, so I leave it slightly open. A closed folder would be the wrong ending. I stand and take the folder to the observation dome one last time. The corridor is quiet. The ship has completed its correction burn and settled into cruise. Through the dome, the Milky Way has moved almost out of frame, leaving a thinner scatter of stars and a long dark field beyond. I set the folder on the console beneath the glass. The universe does not display its ingredients the way a mineral sample does. It does not offer a label. It offers relic radiation, expansion, elemental abundances, distorted images, galaxy motions, cluster collisions, spectra, maps, and tensions between measurements. We assemble the inventory from those traces. We revise it when better traces arrive. There is comfort in that, though not the comfort of final answers. It is the comfort of a method that can keep working in the dark. The ordinary matter in the ship remains close. The console under my hand, the glass above me, the air moving through vents, the cooled tea waiting on the desk. The dark matter remains unseen but gravitationally present, part of the galaxy's larger mass distribution. Dark energy remains even less tangible, a term in the equations that describes the acceleration of the cosmic scale. Radiation from the early universe passes through the scene. Neutrinos do the same, almost entirely unnoticed. Everything in the file is here, in some form, even in this small, imagined room. I look out for another moment and let the scale settle. A star is ordinary matter under gravity, shining because nuclear fusion changes its core. A galaxy is ordinary matter embedded in dark matter, evolving inside a larger web. A cluster is galaxies, plasma, and dark matter bound together. The expanding universe is all of it, averaged across scales, with dark energy shaping the late-time motion of the whole. None of these statements removes the mystery. They make the mystery sharper. That is often what good evidence does. It does not erase the unknown. It gives the unknown a border. The border tonight runs around 3 open problems. Where are all the ordinary baryons in the nearby universe, and how completely can we map their phases? What is the dark matter? Why is the expansion accelerating, and is lambda truly constant? These are not small housekeeping questions. They sit near the centre of modern cosmology, particle physics, and gravity. Still, the file is not only a list of unsolved problems, it is also a record of extraordinary success. We can measure the afterglow of the early universe. We can infer the amount of ordinary matter from nuclear reactions in the first minutes. We can map invisible mass through lensing. We can detect a fossil acoustic scale in galaxy clustering. We can discover that the expansion is accelerating by comparing exploding stars across cosmic time. We can build instruments that test whether the simplest explanation still holds. The universe is not transparent in every way, but it is not silent. I take the folder back to the office and place it on the desk. The lamp's warm circle catches the title one last time. What is the universe made of? The answer below it is no longer a line. It is the whole route through the ship. Office, dome, environmental bay, navigation deck, archive, engineering gallery, cartography lab, sensor bay, bridge, observation well, and back again. Each room gave the file a different handle. Matter you can touch, matter you can weigh, energy you infer from expansion, radiation you read as a relic, neutrinos you count by their influence, evidence you trust because it connects. I close the folder as far as the papers allow. A few pages still press against the cover, keeping it from lying flat. That is fine. Some cases should not close cleanly. Outside, the ship continues through a universe whose visible lights are only a beginning. The stars shine from ordinary matter. The galaxies turn inside dark halos. The clusters bend the paths of light. The space between unbound galaxies expands under the influence of something still not understood at the deepest level. The old microwave background cools as the universe grows. The acoustic pattern remains in the maps. The surveys continue. The detectors wait. And on the desk, beneath the observation dome, the file remains within reach. For now, the working answer is this. The universe is made of the matter we know, the matter we have not identified, the radiation that remembers the hot beginning, the neutrinos that pass through almost everything, and the dark energy or cosmological constant that appears to govern the late expansion. The familiar part is real and precious, but it is not the majority. The unseen part is not optional. It is written into motion, light, distance, and time. I turn off the desk lamp. The folder falls into shadow. The window keeps the stars. The case is not closed. It is measured well enough to keep going.